So we have different definitions for d of t on the left and the right. And let's say that d is distance and t is time. So this is giving us our distance as a function of time. On the left, it's equal to 3t plus 1. And you can see the graph of how distance is changing as a function of time here is a line. And just as a review from algebra, the rate of change of a line we refer to as the slope of a line. And we can figure it out. We can figure out, well, for any change in time, what is our change in distance? And so in this situation, if we're going from time equal 1 to time equal 2, our change in time, delta t, is equal to 1. And what is our change in distance? We go from distance is equal to 4 meters at time equals 1 to distance is 7 meters at time equal 2. And so our change in distance here is equal to 3. And if we want to put our units, that's 3 meters for every 1 second in time. And so our slope would be our change in our vertical divided by our change in our horizontal, which would be change in d, delta d, over delta t, which is equal to 3 over 1, or we could just write that as 3 meters per second. And you might recognize this as a rate. If you're thinking about your change in distance over change in time, this rate right over here is going to be your speed. This is all a review of what you've seen before. And what's interesting about a line, or if we're talking about a linear function, is that your rate does not change at any point. The slope of this line between any 2 points is always going to be 3. But what's interesting about this function on the right is that is not true. Our rate of change is constantly changing. And we're going to study that in a lot more depth when we get to differential calculus. And really, this video is a little bit of a foundational primer for that future state when we learn about differential calculus. And the thing to appreciate here is think about the instantaneous rate of change someplace. So let's say right over there. If you were to think about the slope of a line that just barely touches this graph, it might look something like that, the slope of a tangent line. And then right over here, it looks like it's a little bit steeper. And then over here, it looks like it's a little bit steeper. So it looks like your rate of change is increasing as t increases. As I mentioned, we will build the tools to later think about instantaneous rate of change. But what we can start to think about is an average rate of change. Average rate of change. And the way that we think about our average rate of change is we use the same tools that we first learned in algebra. We think about slopes of secant lines. What is a secant line? Well, we talk about this in geometry. That a secant is something that intersects a curve in 2 points. So let's say that there's a line that intersects at t equals 0 and t equals 1. And so let me draw that line. I'll draw it in orange. So this right over here is a secant line. And you could view the slope of the secant line as the average rate of change from t equals 0 to t equals 1. Well, what is that average rate of change going to be? Well, the slope of our secant line is going to be our change in distance divided by our change in time, which is going to be equal to, well, our change in time is 1 second. I'll put the units here, 1 second. And what is our change in distance? At t equals 0, or d of 0 is 1, and d of 1 is 2. So our distance has increased by 1 meter. So we've gone 1 meter in 1 second. Or we could say that our average rate of change over that first second from t equals 0 to t equals 1 is 1 meter per second. But let's think about what it is if we're going from t equals 2 to t equals 3. Well, once again, we can look at this secant line, and we can figure out its slope. So the slope here, which you could also view as the average rate of change from t equals 2 to t equals 3. As I already mentioned, the rate of change seems to be constantly changing, but we can think about the average rate of change. And so that's going to be our change in distance over our change in time, which is going to be equal to, when t is equal to 2, our distance is equal to 5. So 1, 2, 3, 4, 5. So that's 5 right over there. And when t is equal to 3, our distance is equal to 10. 6, 7, 8, 9, 10. So that is 10 right over there. So our change in time, that's pretty straightforward. We've just gone forward 1 second, so that's 1 second. And then our change in distance right over here, we go from 5 meters to 10 meters, is 5 meters. So this is equal to 5 meters per second. And so this makes it very clear that our average rate of change has changed from t equals 0 to t equals 1 to t equals 2 to t equals 3. Our average rate of change is higher on this second interval than on this first one. And as you could imagine, something very interesting to think about is, what if you were to take the slope of the secant line of closer and closer points? Well, then you would get closer and closer to approximating that slope of the tangent line. And that's actually what we will do when we get to calculus.